Hi, this is the video on revision for multiplexers in digital system. Throughout the lecture, I will also show you how to use example coding in Verilog to describe multiplexer. What is multiplexer? Multiplexer is a combinational logic that functions to select one out of many data inputs to be forwarded to the data output. It is also known as mux. So example, we have a multiplexer in the system where there are 4 selections. And the first selection is the audio coming from MP3, the second selection is the audio coming from laptop, sound card, and the third as shown, and so on. So multiplexer will allow the user to choose which audio source to be forwarded to the sound system to be played. So this is one example about multiplexer. So we have 2-to-1 multiplexer if in the system you only need to select one out of 2 items. We have 4-to-1 if you have 4 items to be selected. And we have input call select input. So that is very important signal to determine which item to be selected to the output. In the example more related to the computer, you may see also multiplexers where it select the functions of the operation. So the selection here involves the addition, subtraction, multiplication, and division. So one very straightforward example that use this concept is the calculator. So at one time you can only use one function in the calculator, right? So the select signal here will be inputted by the user when you want to choose which function to use. So the answer of the operation, whether it's addition, subtraction, or multiplication, or division, will be displayed at the output of the calculator, thanks to the selection done by the multiplexer. So you have learned in the basic course in electronic design, digital electronic design, 2-to-1 multiplexer can be designed in a schematic method where it consists of the two AND gates, inverter, and OR gates as shown in this figure. You also can use Verilog to design or describe the 2-to-1 multiplexer. If you use Verilog language, so you can choose to use a different coding style. You can have several options as shown here, because the Verilog coding style is divided into structural coding style that describe the structure of the circuit, for example the circuit shown here, or it can be behavioral coding style. So under behavioral coding style, you can choose to use the continuous assign statement or procedural statement that involve always block. So let's look at the simple way to describe 2-to-1 multiplexer using a structural coding style. So you can call the standard primitive gates library available in the Verilog compiler to build the simple circuit of the 2-to-1 multiplexer. So as we know, the multiplexer function table can be described this way, where the input part is the select signal S, and the output column lists out the output of the multiplexer. So when S equal to 0, the output will follow I0. When S equal to 1, output will follow I1. So when you use the primitive gates library available in the basic Verilog tools, then you can instantiate or call out the gates you need. So for example, here you need 2 AND gates. Then you call out the AND, or this action is called instantiate. You instantiate 1 AND gate, 2 AND gate. So the first AND gate will connect to output A. So this is the output of the first AND gate, connect to wire A. So you connect to wire A, and it read in the signal I0 and signal from wire C. So I0 and wire C. So if you use the primitive gate library, then the first parameter should be the refer to the output port of the gate. So this parameter refer to the output port of the AND gate. That's why it's connect to the wire A in this example. The second AND gate connect the output port to wire B and read in the signal from S and I1. S and I1. And the OR gate read in A and B and produce output C. Whereas the inverter read in the signal S and produce C as shown here. So these 4 lines in the Verilog code represent the 4 primitive gates here. Since all the gates work concurrently. So the ordering of these statements can be changed. So it doesn't represent the sequence of the gate operation. Alternatively, you can use continuous assign statement to describe the logic operation in the 2-to-1 multiplexer circuit. So you can with using continuous assign statement, you have to start with the assign keyword here. So the first line, similar to the previous slide, the first line, each line here represent or describe the basic logic operation. So the first line describe the inversion. Okay, so you can write C equal to S bar. Okay, so in Boolean operation you use C equal to S bar, but in Verilog you use the symbol tilde to describe the inversion. C equal to tilde S or exclamation mark S, also okay for the single bit operation. The second line here describe the AND operation of corresponding to this AND gate. It is I0 and with S bar. It is I0 and with the S bar signal, which is C. Okay, and the third line describe the AND operation of the lower AND gate there, and the last line represent describe the OR operation of this gate. So all operations should be using the stick symbol. There's a typo here. So there are more other operators you can use in Verilog. So it allows you to describe a wide varieties of operations in the hardware. See, the first row contain the symbols that they are used to describe the arithmetic operation. So plus means addition, percent sign means modulus operation, double asterisk means the power operation. Okay. So the second row operation lists the symbols representing the bitwise logic operation. Like the tilde allow you to do the inversion, to perform the inversion on multiple bits of the binary numbers. Okay. Same goes to the AND, NAND, OR, NOR, XOR, XNOR. The last two mean the same thing, which is XNOR. Unit reduction is the reduction operation on multiple bits to produce the single bit output. So if you use ampersand here, perform the ampersand or AND reduction on say 8 bits, then the operation of the reduction will AND all the bits in the 8-bit stream there and produce the result as a single bit. Okay. Logical, normally symbols of logical is used in the condition to check the true or false of the condition. Okay, and so on. You can see here the equality for the comparison, relational also for the comparison, and followed by the shift, logical shift, arithmetic shift, concatenation to concatenate two signals becoming one signal. For example, you put A, B inside, that means you combine A and B become a longer stream of the data. Replication, repeat the bits you put in the inner braces here. So let's say you put 0, 1 inside, and then you put 3 in the here, then it means you repeat 3 times the 0, 1, which becomes 0, 1, 0, 1, 0, 1. And the last one is conditional operator that allow you to describe the scenario of if-else using the assign continuous statement. So now let's look at a conditional operator usage in describing the 2-to-1 multiplexer. So until here you see there are 3 ways to describe the same circuit. You will see more in the examples later. So if you use a conditional operator to describe the 2-to-1 multiplexer, as you can see in the truth table of the 2-to-1 multiplexer here, it is can be described in the if-else way, where if S equal to 0, then out will take the value I0. If S equal to 1, then out will take the value of I1. So more accurately, this out should be corrected to C, to make it the name the same as the name shown in this symbol where the output is Z, and also the circuit here. Okay, so if S equal to 0, Z equal to I0. Okay, so this can be described in the if-else way. So here, that is how we describe using the conditional operator. We put Z equal to what? Z equal to I1 or I0. It depends on the condition, whether the condition is true or false. So how to read this statement? We read this way: Z equal to I1 if S is true. Okay? Z equal to I0 if S is false. In other words, Z equal to I1 when S equal to 1, Z equal to I0 when S equal to 0. Okay. So okay, the last method to describe the 2 to 1 marks is using procedural state that involve always block. So when you use procedural state, you'll need to start with always applies construct followed by a bracket that lists down the sensitivity parameters. So what to be listed in sensitivity? These are those signals that determine the output of this always block. So this always block is written to generate the signal Z. And as you can see, signal Z is put at the left hand side of the equal sign. So what determines signal Z? If we look at the block diagram of the 2 to 1 marks, signal S, I0, I1 are the signals that determine signal Z. So those are the signals to be listed in the sensitivity list. So after you complete the line of the always block header, then you can write the behavior of the 2 to 1 marks using if else. So if S equal to 1, then Z will be equal to I1, else Z will be equal to I0. Procedural statement allow us to describe the behavior of the circuit in a sequential way. So it means, in other words, it describes an execution of a logic in sequence. So when you write the logic behavior under the always block using more than one statements, then you have to enclose the statements with begin and end. And the statements inside will be executed in the sequence you write. So if you write Z equal to I0, then when execution of these lines, so Z will be assigned I0 first, then only the statement of if S equal to 1 will be checked, and then if S equal to 1 is true, then Z will be assigned I1. So it is like a programming style of coding. So this coding also describes 2 to 1 multiplexer. Okay? So the difference between left and right is the left side only consists of if-else statement, which is considered just one single statement, whereas the right one, if you change to this way of coding, then it consists of one statement, the initial value of Z, and the if statement is considered the second statement. You also have multiplexer that read in 4 items and select one item to be forwarded to the output, and we call this multiplexer 4 to 1 multiplexer. And I believe you have learned also how the structural logic circuit look like for the 4 to 1 multiplexer. So again, there are many ways to describe the circuit in Verilog. So you can use structural coding, where you can show the connection of all these basic gates using the primitive gate library of the Verilog. Or you can again use structural coding by using modular way, where you first design 2 to 1 multiplexer, then you use 3 units of the 2 to 1 multiplexer to build 4 to 1 multiplexer. So when you build using these 3 units of 2 to 1 multiplexer, you connect them in a structural way. That's why it is under the category of structural coding. Continuous assign statements also can be used. So you can do that using describing the logic using Boolean expression or using conditional operators. Okay, or procedural block using if-else statement or case statement. So let's look at only the few of 4 of them in this lecture, because I think like connection of the basic gates will be similar to what I have shown in the 2 to 1 schematic circuit, and then a Boolean expression also similar to the 2 to 1 example. So I will skip these two and focus on the modular design using 2 to 1 marks, conditional operators, and procedural statement. Okay, so now how do we conduct the modular design for 4 to 1 multiplexer using 3 units of smaller multiplexer or 2 to 1 multiplexer? So first we describe them hierarchically from top to bottom. So this is how the top level of the 4 to 1 marks block diagram look like, where it consists of data input A, B, C, D, and select signal. Select signal should be 2 bits, be based on the log based to the number of items to be selected. And to build using 3 units of 2 to 1 multiplexer, we put the first 2 units of multiplexers so that the inputs of the multiplexer are connected so that they are receiving the input data A, input data B, input data C, input data D, starting from the least significant data input. The select signal of both the multiplexer will come from the select signal least significant bits, which are select 0. Okay. So when select 0 is 0, so A and C will be selected. When select 0 is 1, B and D will be selected. The third multiplexer is put at the second layer so that this multiplexer will choose between the data forwarded by the first multiplexer and the second multiplexer to be forwarded to the output. And the select signal will be controlled by the most significant bit of the select, which is select 1. Okay? So when select 1 is 0, select 0 also 0, that means 0, 0. So by right, A will be selected. So let's check. When select 1 is 0, this is selected. Select 0 is 0, this is selected. So yes, A will be selected and forward to the output. So here, because you need to connect the output of the multiplexers to the input of the third multiplexer, you need the internal connection, or what we call wire. Okay, now to design in a modular way, first we need, after we hierarchically describe the 4:1 mux, we know that the basic component we need is 2:1 mux. So there are 3 identical units of the 2:1 muxes we need. So first we need to design the basic component here. So you can use any style of coding you like, and you design 2:1 mux. So you need 3, but you just need to design once, because the 3 unit here is just the 3 copies or instances coming from the same type of design. So after you successfully describe the 2:1 mux, okay, so before I further explain how to describe the how to connect the 3 units of the multiplexers, let me do a quick revision on the coding for the multiplexer 2:1. So first, when you want to describe a module, say for example here multiplexer 2:1, first you need to declare the input and output ports. So you declare using this format where you start with the keyword input or output depending on the type of the ports you want to declare here. Input followed by the name of the input. For example, here we have select S, I0, I1, and then output Z. So this O should be small. Okay. Then you can use any coding style you like to describe the behavior of the 2:1 mux. Okay. So if you have multiple bits, say your I0 or I1 consists of 4 bits, then you have to use the multiple bits or vector way to declare the inputs and outputs. But in this example, we assume it's 1 bit or scalar. Okay, so the module start with the keyword module followed by the module name. Okay, so now let's move to the mux 4:1 project here. Okay, so when you want to describe mux 4:1 module, so similar to what you have done in the mux 2:1, you start with the module keyword followed by the name of the module. Okay, and then the input output and declare them. So in this case, the 4:1 mux should have 2-bit select and signal, so you can use the vector 1 down to 0 to declare the select input. Okay, followed by again this is small I, followed by input A, B, C, D, and output out. And remember, we need 2 internal connection or wire, so you also need to declare them at the beginning of your coding. Okay, using keyword wire followed by the name of the wires. So here now come to the structural part of the mux 4:1, where in structural description you need to describe how these 3 multiplexers are connected. So now let's instantiate the first mux 2:1. So you instantiate by calling the module name. So the module name refers to the mux 2:1 module name, which is mux 2:1. Okay, and then followed by the instance name. So this is the first instance you are writing here. So just name it as what you wish, and in this case, let's take M0 as the name. So after module name, followed by instance name. Okay. After that, followed by the signals you have declared in this mux 4:1 to be followed by the signals connection to the multiplexer M0. So as you can see in this diagram, so M0 will connect to signal A of this module. You have signal A, B, C, D, and select. So M0 will connect to signal A, signal B, and select 0, and wire N0. Okay. So select 0 will connect to S. Okay. Why the first signal you need to put select 0? Because the first element here showing the connection of the signal to the first port defined in this MUX 221. Okay. The first port defined by in MUX 221 is the select port. Okay. So this design requires us to connect the select 0 to select port. That's why we will put select 0 first, not other signal A, B, C, or D. Okay. Followed by A connecting to I0. Why? Because the A of this MUX 421 is connecting to I0 port of this 221 MUX. So the second element referring to the signal A connecting to I0 port of 221. Okay. Followed by the B to port I1, and followed by the N0 wire coming out from the port C. Okay. Similarly, you do it, describe it for the second, the M1 instance and also M2 instance. So by doing this, actually you have described all the 3 2-to-1 muxes and how they are connected to complete the design for 4-to-1 mux. In case you have wider data width, okay. So just now we talked about 4-to-1 mux, but each of the data consists of 1 bit only. But there are many situations, many times you need each of the data item consists of multiple bits. Right? So in this case, it is a 4-bit data item. Okay. So in this way, in this case you need to use the vector to describe the ABCD to be 4 bits. Here it consists of bit 3 down to bit 0, totally 4 bits, and out also 4 bits. Alternatively, the input-output declaration can be combined with the input-output list in the bracket after the module name. Okay, so you can take out the input followed by the vector, and then followed by the select port name. Okay, input followed by the vector A, B, C, D. Okay, why we have 2 times of input repeating here? Because these 2 set of inputs having different data width, so you need to declare them twice. You need to write input twice, but each is for the different input signal. Okay. Then lastly, the output out. 4-to-1 mux also can be described using the conditional operator, where the conditional operator will need you to put the condition expression first, followed by question mark, followed by true statement, column for false statement. Okay, so if you look at the truth table or function table of the multiplexer, 4-to-1 multiplexer, so it's like a if-else concept, right? So if-else description. If select equal to 0, then out equal to in 0. Else, if select equal to 0, 1, then out will take in 1. Else, if select equal to 1, 0, out will take in 2. So with this, you can describe using continuous assign statement using conditional operator. Out, will be equal to the condition followed by the statements of true statement and false statement. So this means select equal to 0 will be checked first. If select equal to 0 is true, then output will take the value of in 0, same as corresponding to this row. Okay. But if this condition is false, then the statement following the column will be checked. So the statement following the column will be the whole thing here, the remaining of this line until the semicolon. So this statement will be checked. So it's kind of nested if-else statement. Okay, so when coming to the false statement, so the condition will be checked again, but this time it will check select equal to 0, 1 or not. So if select equal to 0, 1, then the in 1 will be taken by the out will be equal to in 1. But if this yellow condition is false, then the following statement after this column will be checked. Okay, then select equal to 1, 0. If true, then out will be equal to in 2. Otherwise, out will be equal to in 3. Okay. Next, let's look at how to use procedural block to describe if-else in the if-else statements for the 4-to-1 mux. Okay. So I would like to highlight here the output is given the type rect. So you can combine the rect with the output declaration, or you can write separately like this. So output is rect because output is the left-hand side variable or signal in this always block. In other words, this always block produce output. So output need to be written under data type rect. So and then the following I think is clear with you with the if-else concept. Yeah. Yeah, as I said, you can also combine with output declaration as one line statement declaration. Okay, lastly, let's look at how to use case statement to describe marks 4 to 1. As mentioned just now, the rec for the out can also be written combining with the output declaration like shown here. Okay, so if you use always block, then you, with the case statement, then what you will write is you put a case keyword followed by a bracket, which is inside there, which is a condition variable. So in this case, the select is the condition that will determine what value will go to out. Okay, so and then you list down under the case statement, we list down all the possible value for select. Okay, so in this case, select is 2 bits, so we have 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so then after the value, each value of the select signal, it is followed by a column and then followed by a statement showing what happened if the condition variable select fulfill that value. So select when equal to 0, 0, the output will take input 0. In the second case, select if equal to 0, 1, output will take in 1, and so on. So if you use case statement, you need AND with the AND case, and you will see the close correspondence of what listed in the case statement with the truth table of the design. That's all for the lecture about multiplexer and how we use Verilog to describe them. Thank you.